Yeah, thanks, Ville, for the kind introduction. The title of the talk is Path to the Future for 77 Years and Counting, and probably you're wondering why. But this talk here today is about societal impact and microelectronics, especially the societal impact of microelectronics to the society that surrounds us. But because the odds for me being here is close to zero, I would like to thank a couple of my former colleagues. I would like to thank Saska Lindfors, Rami Ahola, Mikko Valtari, Lauri Koskinen for dragging me forward when I most needed it. I would like to thank Ari Paasio and Mika Länsirinne for teaching me some of the professions that Ville mentioned. And I would like to thank also Mr. Dean, Professor Jussi Ryynänen, if he's somewhere here. You are probably even more excited about this occasion than I am, because I can say whatever. Then, of course, I can't forget this. I have to thank my wife and lovely daughters. They're probably looking at this somewhere, and they see that their pet orangutan has been left on the stage now alone, so please come and rescue me. Anyway, let's go back to the actual thing of the day. So shortly a background, which was societal impact in relation to microelectronics. My maternal grandfather was a professor in sociology. And from my mother, I heard lots of stories about how great it is to be a professor and how great impact you can make into society if you are one. So that's a special meaning for me today. Then my father was a civil engineer, a road designer. He graduated from Helsinki University in Technology in '64. And he taught me two things. First one was that, this is a message that I would like to convey to my students if you are in the audience, that you should be so routined in math that you can do that with your spinal tap, so that you can reserve your brain for thinking. And the other thing is that your life is very interesting if your work has some kind of a societal impact. And when I was doing year 2006 about my doctoral thesis, I thought that I missed it totally, because I was pondering with the problems like how does the picosecond timing inaccuracy in digital to analog converters affect the behavior of the microelectronic circuit. And this is a topic that interests basically no one. Or are you interested in it? You haven't probably even heard what is digital to analog converter. Some of you have, I hope, my students, for example, and you probably have also heard sometimes about that. But that was a problem. I didn't see any meaning in the research. And lately I learned something different. Before I go there, I would like to ask you, have you probably held this kind of a device in your hand? It's called mobile phone. You probably have seen it. It's an interesting device. You can actually carry all the information generated by human societies in it. Still, you can take pictures of kitten with it. But it's, if your dog eats it, the bugs come out, and those bugs are the things that we work on. That is microelectronics. It makes these things run. Then the other thing that I have with me, this is laptop. It has more of those bugs inside it. It's also full of microelectronics. And the latest thing that I found out is this one. All we are civilized people, so we have a huge bookshelves in our home, although I don't, or it's full of comic books. But you can pack 24,000 books in this device. It's pretty nice. You can also make notes of it. And it's also full of microelectronics. So yes, microelectronics probably has some kind of effect on the surroundings that we are living and in the societies that we are building. But let's see how it started, because we always want to create some great impact now. But that's not the case. Well, the journey is way longer than we hope. This handsome guy here is Gottfried Leibniz. He lived in 17th century, and around 1690s or 1689 he invented binary numbers, those long strings of ones and zeros that you use or see in the TV when you see computer programs running there, or in Matrix movie or something. And Recently, after that, it took only a couple of 100 years. Charles Babbage, English engineer, started to build a computer, mechanical computers first. He tried to automate computations, specifically computations of logarithms, because he had logarithm tables that he was sure are full of errors because they were constructed by French people and he was British. And he tried to make a machine that calculates the logarithms correctly. And at the same time, Ada Lovelace, you probably have heard of her, started to do computer programs to these machines. Neither machines were built during their time, but still, they developed the theory of modern computer engineering and computer science. Then George Boole, 1850, he stole something from philosophers, which was logic, notion of logic, and converted that to math. Developing Boolean algebra, which is now the foundations of one of my digital microelectronics courses. I teach there Boolean algebra because that is the foundation how to construct digital microelectronics. Then something really interesting. This, I say that this is a good example of a master's thesis. It's a master's thesis of Claude Shannon, a symbolic analysis of relay and switching circuits, 1937. He combined the theories of Gottfried Leibniz, the theories of George Boole, to the fact that you actually can provide notion of ones and zeros with switches. You can create machines that build logic functions with relays and switches. He went on with the information theory, but this was his master's. So if you are willing to do masters, please beat him. It's a good objective. You probably get some fame and money out of it. But then, this is the year that I started counting. I hope that I counted correctly. 1947 was first transistor was invented. And this is remarkable invention in a sense that now we had the final missing piece of a thing that had been built over 200 years, which means an efficient switch. So we had binary numbers, we had idea of mechanical computing, we had theory of Boolean logic, we had theory of doing logic with switches, and now we had good switch. So things went on. About 10 years after, somebody noticed that, okay, we can put many of these on the same piece of substrate. Also integrate other electronic circuits on the same substrate, like resistors and capacitors and so forth. Those are integrated circuits. I was appointed as an associate professor of integrated microelectronics, and this is the thing. But this had only few components on it. So the development went on. It was quite slow in the beginning. Planar integrated circuit. We had a couple of transistors. Possibility to create routing on piece of silicon, a piece of substrate. The substrates were not silicon back then always, but I think this is gallium arsenide or gallium substrate. But anyway, in the planar integrated circuit. So the manufacturing theory was there now, or also the practice, how to make circuits. And then in 65, this thing you have heard, Moore's law. Gordon Moore said that the number of transistors will double every 18 months on one integrated chip. Okay, if you have two of them, it means that 1.5 years later you will have 4. But around these days, we have something like 50 billion transistors on a single piece of silicon. It's quite many transistors. And if you think of what you can do with these transistors, it's amazing. We have artificial intelligence, we have machine learning, we have implementations of math. You can think, if you are doing signal processing, you can think yourself computing fast Fourier transforms manually on pen and paper. Or virtual realities that we can create with these transistors. Or the services we can run on the computers that we have. So basically, our whole society is built on these 15 billion transistors on tiny chips, which are a couple of millimeters square. So how this is related to Aalto University? We have been doing these microchips in Aalto University and Helsinki University of Technology since '88. First in something that is called MEPSI, the rabbit here. It's a Microelectronics piirisuunnitteluyksikkö funded by Professor Veikko Porra and Kari Halonen, who is still working with us. And we have been doing chips, as you see here. There are base station transmitters, mobile phone components. You have probably heard about a mobile phone company called Nokia. Many of their engineers were educated in our lab. And we continue to do that for a good reason. This is the list of companies on 21 most valuable companies in the world, measured by their value in stock. And what is common there is that 9 out of 10 are doing microelectronic chips. What is also visible there is that none of them are European. The one that is not highlighted is actually an investment company. Then what is also a fact is that you see us 210 times a day, but you still don't know who we are, because we are invisible guys inside this device. But we have some societal impact. And I would like to end with a positive note that tells us what this is all about. This is a photo taken by Voyager. The pale blue dot there is Earth. It's 6 billion kilometers away from here. And the dot there you see is Earth, our home. And Finland was just chosen again, 7th time in a row, the happiest nation on Earth. We are living, everyone living here is member of this society. And this picture says that we are happiest nation in the known universe. And this is built by the wise people after the Civil War that took some effort to actually build a society and understood that it's not about victory, it's about prosperity and peace. And currently we are also living times of turbulence. We have war in Europe, and we have also something that is called chips war. The chips war is something that Europe is running behind. United States has great investments in doing microelectronics design. They invest hundreds of billions of dollars to that annually. Also, South Korea, Japan lately, China, and Europe is severely running behind. So in order to have prosperity and welfare, we have to compete in this competition in order to be a credible partner, so that we can do, for example, European computers, European microelectronics, European mobile phones, European customer electronics, because that brings us prosperity and peace. Thank you.